Let's build a versatile breadboard for microcontrollers like the Arduino Nano or the ESP12 today. Like these ones which I've made for some of my videos. This one I made for the RFID keypad reader video, and I made this one for the Tasmota garden watering video. I'll show you a couple of little tricks and adjustments that make building your prototypes much easier and allow you to power everything with a single 12 volts power supply. Hey guys, I hear you ask, why would I want to use a breadboard? I have my Arduino Uno or my Wemos D1 and I can build everything using jumper cables. Fair point. Those systems are great when you're starting with microcontrollers or if you want to test software functions. You may in fact use these systems and wire everything with those jumper cables. But have a look at this. I'm sure you have experienced the same already. If you're building more complex devices with more external components, then things can become quite messy. There are wires everywhere, and therefore debugging and resolving errors in cabling can become a lengthy and unpleasant task. On top of this, in my opinion, the jumper cable version is great for planning and testing, but not so great if you want to actually run the device on a daily basis. For this, it would be much greater if everything was on a printed circuit board, a PCB. I will make 3 episodes on actually designing and building these. This here is an example of a PCB that I have made for a radio-controlled word clock. Unfortunately, I can't show the clock here because the design is copyright protected. But even if you are not planning to create a PCB, then a breadboard adds a lot of value to your design. Clearly, if you look at it, there are fewer wires and the whole thing looks much cleaner. But let's go step by step. If we look at a typical breadboard like the ones I'm using, then you can see that there are many clips where you can plug in jumper cables, connectors, electronic components such as resistors or diodes without soldering. There are typically 2 or 3 4mm connectors on top where you can connect your power supply to. If we look at the layout on that board, you can see that the pins or clips are connected in a certain way. First, there is the vertical connections. They go in those 2 lines here from the middle of the board to the end. In each column, there is 2 of them, 2 at the top and 2 at the bottom. In between, there are many more horizontal connections with 5 pins each. So each row of 5 is connected. The idea behind this layout is that you can plug in your components into the horizontal rows and then pull connections to the vertical lines as needed, where you would normally provide power or ground, like I do here with this Arduino Nano. I have the Nano here, I have a 5 volt power supply, and I want to wire these. First, I pull a simple wire from the connector on the top to one of the vertical buses. Same for ground. Then I plug in my Nano into the horizontal rows and can then pull those small jumpers to the right pins in order to power my project. This works well because the Nano is breadboard friendly and it works with 5 volts. Other components are not always breadboard friendly. Look for example at this device, which is impossible to use here because the pins are too close. You will need an adapter plate. But even devices which seem to be breadboard friendly are not really usable without modifications, such as this ESP32 or this Wemos D1 Mini. They just cover too many pins, leaving me with no space for extensions. If I wanted to use this ESP12 from Espressif, then things are even worse. There are no pins to connect at all, because this is a surface-mounted device SMD. So let's deal with the larger modules here first. In fact, these cheap breadboards here can be unmounted quite easily. If we turn it around, you can see that the plastic part on top is fixed with a couple of screws on the bottom. I have already removed most of them, let me just remove the last 2. As you can see, the plastic part actually consists of multiple single parts which are fixed on this additional adhesive cover. So what I did, I just cut the cover along one of these smaller columns, and now I can take the whole thing apart. The columns are in fact put together with these little clips that fit exactly into the slots of the next piece. So let's just take this small column out and put it to the outer end. Let's then connect the two remaining elements, and what we get here is two row elements separated by one column element rather than being separated by two. So we have two row elements which are really close together, which would work well for the Arduino Nano, and we have another two row elements which are a bit farther away from each other. And those will actually work very well for the whole ESP32 and Node MCU elements. I might even take it further and move the outmost right row element to the left, and would then have maximum flexibility in spacing. Cool. Let me just put this back together quickly. While I do this, that might actually be a great moment to take a second to quickly hit that like button. And if you feel like, hey, this stuff is interesting, why not hit the subscribe button? It's free of charge. And if you click on the bell button, then YouTube will automatically tell you whenever Mark made a new video. This way, you will never ever miss out on an episode. Thanks guys, much appreciated. When you're doing projects with microcontrollers, you might encounter another challenge. And that is that you will probably need multiple different voltages. For example, in my Tasmota garden watering video, I needed 3 voltages. 3.3 volt for the microcontroller, 5 volts for the relay boards, and 12 volts for the valve. Now, if you have a modded ATX PC power supply like this one, yes, there is a video on this, check the little info card in the upper right corner of the screen, then you are well off, because it provides exactly the voltages we need for our project. However, not everybody has these, and for day-to-day operations later, you don't want your lab bench power supply connected to the device all the time. Many people power their projects over the USB bus, and that does lead to a lot of issues. The USB port and even many USB chargers sometimes cannot provide enough power to power everything, especially if you're using Wi-Fi. Most of the problems and calls for help that you can read on the forums in the internet are related to bad power. If the power supply cannot cope with the charge, then very strange symptoms can appear. And they cannot necessarily be related back to the power supply being the source of that behavior. It is, however, quite easy to get hold of a decent 12 volt supply with, let's say, 2 amps power. They are widely spread for so many devices these days. Or you might have a lab bench power supply that can most probably provide 5 or 12 volts. So here's what I've been doing in order to get this sorted. I have purchased a couple of these cheap DC-DC step-down converters. That is a ready-made printed circuit board with an LM2596 chip. That circuit can regulate the voltage from 1.5 to 37 volts. It's got a reasonably good efficiency, and these boards come with 2 capacitors, one at the input side, one at the output side, and also a little spindle potty that you can use to adjust the desired voltage. All you have to do in order to make these breadboard friendly is solder pins to the input, output and ground line, and then you can plug them onto the breadboard and pull wires to the vertical lines, which makes it possible to connect to any device on the board. They are easily available on the usual platforms such as eBay, Amazon, Alibaba, AliExpress or Banggood, and go from $1 to $5, depending on where you buy and how many. I'm also using a cheap 3.3 volts converter behind the 5 volts, which gives me the voltage level I need for the expressive microcontrollers. Cool. So we could connect 12 volts to the large connectors on top here, and we would now have 3 voltages available on the board, 12, 5 and 3.3 volts. Now let's have a look at how we can make this ESP12 module here a bit more breadboard friendly. Special adapter boards like these ones are available for these chips. They typically sell for $1 or so. All you have to do is solder the ESP on the board and in a second step solder pins below so that you can connect to the breadboard. I have not checked, but I'm sure that you can get them pre-soldered as well if you spend a bit more money. The cool thing with these boards is that they have room for a 3.3 volt regulator on the bottom. So if you wanted to power everything with 5 volts and taking the necessary precautions, you could do with one single voltage on the board. All you have to do is solder the right regulator on the adapter board and maybe remove a little SMD resistor from the board. This board here is an example. I have also added a capacitor to cover for current fluctuations. They come in various different flavors and colors, some with the SMD devices soldered and some without. I admit it does require a bit of patience to put these together, but it is totally feasible. I like these boards and I'm even using them in finished projects because that way I do not have to do two-sided PCBs, but I can rather work with a classic hobbyist-friendly one-sided version. Furthermore, I can put resistors or other flat components between the adapter board and the main PCB, which in fact saves even more space on the PCB. Great, so now we have modified the breadboard, we have made the components breadboard friendly, and we have a good power supply. But two things are still missing. In order to program the ESP microcontroller, we need two buttons, one for reset and one for programming mode connected to GPIO 0. Moreover, we need some interface in order to connect to our PC and transfer the software onto the microcontroller. I have recycled these small push buttons here from some scrap electronic device and they do their job just perfectly. If you are using a Wemos D1 Mini or an Arduino Nano, then you don't have to worry about an interface for programming, as they come with a USB port. But if you are using the ESP12 boards or the Arduino Mini, then there is no USB port, so we need to add it. You might ask, why would I want to do projects with such devices? Wouldn't it be easier to use the version with USB on board? Well, think of two aspects here. One is power consumption. Every element on the board consumes power. If you wanted to build, let's say, a solar-powered soil moisture detector that is switched on every hour, quickly sends the moisture data over the Wi-Fi and then goes back into deep sleep to save battery, then every microamp counts. So you don't want additional elements. A second aspect could be that you need the serial port of the device free and that the USB interface could actually interfere with it. Either way, that USB port can be added by using a UART board like this one. Those UARTs or USBs, USB to serial interface, come with different chips, such as the CH341 or CH340 in the El Cheapo version, or with CP2102 or FT232 chip in the more expensive flavor. Anyhow, you can easily stick the UART module onto the breadboard and connect to the RX and TX connectors of the microcontroller, like I do here with those two purple wires. That's pretty much it. We're ready for the next project. We have a versatile board with 3 voltages, a microcontroller, a USB interface, and still a lot of space left on the board for additional components. Actually, I have 2 breadboards and I always leave one of these readily configured and use a second board for experiments. In conclusion, I can say that I experience much more joy and much less frustration by using a breadboard, because errors are much easier to find and the whole thing just looks more structured and clean. For the best experience, I recommend that you get one of these jumper cable kit boxes. They are ready-made for various distances on the board and have a much better grip in the pins. So to sum up, if we look at the shopping list, here is what you will need. A breadboard which costs around 10 to 15 bucks. 1 or 2 step-down converters for, let's say, a total of $7.50. and 2 jumper wire kits, one for the board and one for longer distances or external devices, for a total of maybe $7.50. The whole totaling up to a maximum of $30. But trust me, the time you save and the absence of frustration makes it totally worth it. Guys, this concludes today's episode. I hope you liked it. If so, please leave me a like on YouTube, leave a comment, tell me if you found this episode useful or not, if you are doing projects with microcontrollers and breadboards. Don't forget to subscribe and enable notifications. Thanks for watching. Stay safe, stay healthy. Bye for now.